And so therefore you'll need to go to week 16 to check it with the key, not the current updated week on Schoology. Also, if you need help on any of those, let me know. I will say I'm not going to spend any time right now going over those. We're going to go ahead and start 10.3. The reason being is 10.3 is almost identical to 10.2. So in learning 10.3, you're going to get practice with the 10.2 stuff. So if you're struggling, the good news is this lesson should help you out. But again, if you still need help, if it's still not making sense, email me, let me know sometime you can meet outside of class, and we'll go from there. The final thing I would do is I saw a lot of people doing this. I love this, highly recommend it. Labeling your problems as you're solving them with the 1, 2, 3, 4, 5, 6, 7, 8 is super helpful, I think, for you and for me. So if you keep doing that, that would be great. Okay? That being said, we are going to kick off 10.3 with a problem. Then once we go through the problem, we'll go through a little bit of theory. Then we'll do a couple more example problems and go from there. So Visa is a credit card company lowering its interest rates by 1%. Again, as always, if you want to get a kickstart on this problem, writing down the key pieces of info, go for it. Records from the rate change. So the average outstanding balance on credit cards to be a population average of $576. So all of the credit cards, they've analyzed them and find on average there's an outstanding balance of that amount. Managers believe that reducing interest rates will spur greater use of the credit cards, which result in higher outstanding balances. To test this claim, a random sample of 36 accounts was examined 6 months after the interest rate reduction. Average outstanding balance was now $615 with a standard deviation of $120. We want to test the manager's claims at 2 levels of significance. Okay, we're not only going to look at, usually we'll look at either the 5% or the 1%. Now we're going to be looking at both. Okay. So what that you can see here is they're reducing the rates by 1% because the credit card company wants people's outstanding balances to be higher. And why you see me underlining what's in red here is this is where your alternate hypothesis comes from. I think some of us are struggling identifying the alternate hypothesis and are just looking at whatever the sample mean is. Okay, we don't want to do that. Just because the sample mean is bigger than the population mean doesn't mean it's a greater than. Otherwise, you're going to get trapped when it's a two-tailed. When I say read the context of the problem, this is what I'm referring to. The managers believe that reducing interest rates spurs greater use, which results in higher outstanding balances. So when I read that phrase, higher outstanding balances, that's where I'm thinking, okay, my alternate is going to be greater than 576. The company wants to increase the balance. So again, we're going to solve this kind of like normal. Again, it'll be a review, get your brain back into 10.2 mode. So what we're going to do is start with the known information. Population mean, 576. Again, if you want to go ahead on your own and go ahead and solve this, we're going to hypothesis test it just like normal. So feel free to do that. Sample mean is 615. Standard deviation, S equals 120. Again, a little footnote I will put up here. Because we're working with a big sample, we can assume that these two things are equal. Okay, that's a concept back from chapter 8. That was actually our first definition in chapter 8. So we can assume these are equal. That way we can run the hypothesis test. Sample size was 36. Again, indicating it's a large sample, which means that can be true. Finally, the mean and the standard deviation of our sampling distribution. Again, that mean is the same as the population mean. Standard deviation is going to be that population standard deviation, which we don't know, but we can substitute that sample standard deviation in instead. And And when we do this, we get 120 divided by the square root of 36 is 20. Okay, so now we're going to write our null and our alternate hypothesis. Again, we have our information. The null hypothesis, again, no news here, nothing new. Despite the change that they made lowering those interest rates, we're assuming that people are using the credit card at these same. Okay, we'll assume no changes happen and see if there is sufficient evidence to say change has happened. What do we mean by change? Well, we got to interpret that in the context of the problem. The managers want to see if people's balances have increased. So if we're looking to see if people's balances have increased, that would mean the average outstanding balance goes up. Again, I can't stress it enough. That is not from the test statistic being 615 or the sample mean being 615. That is from the fact that they want to see if the outstanding balances have increased. Level of significance. At this point, we're going to run two levels of significance here. They want us to test both. We'll skip the potential errors from now. I think we've spent plenty of time talking about those. Again, type 1 error, reject the null when we shouldn't. Type 2, fail to reject when we should have rejected the null. And again, if you're someone who is struggling with explaining your errors, I will happily help you with that. But since we covered it a lot in 10.2, we'll skip that part for now. Type of test. We're looking at a right-tailed test. Again, this comes straight from the alternate hypothesis. Alternate says our mean is bigger than 576. Since it's bigger, we're looking at a right-tailed test. Yeah, nothing new, really. Critical region and critical value. This is where we have to keep in mind that we're running two tests. So steps 5 and 6, we're almost going to have to run twice because we have two critical regions, okay? But for the sake of argument, and if you want to do this on your paper to make it a little simpler, I'm going to draw them on one graph. I actually think it helps the visual. So remember, how we run a hypothesis test is we look at the distribution of sample means. We do have one specific sample mean, that's 615. But the idea is if we took a different sample of size 36, we could get a different sample mean. All these different sample means make a normal distribution because the sample size is bigger than 30. That was chapter 8, central limit theorem. Because we're going to assume the null is true, this is going to be the distribution assuming the null is true. The mean would be, the middle of this curve is 576. We assume the null is true, that means the mean of all these outstanding balances is 576. We know that the population mean is the middle of our distribution of sample means. For now, we'll start with 5%. So in red, our one level of significance is 5%. Combining the idea that this is a right-tailed test and our level of significance is 5%, the idea of the hypothesis test, does our data value, our sample mean, if it falls in the top 5%, we'll reject the null. If it doesn't, we'll fail to reject the null. Again, I know this is review for a lot of you. I know you're going back through. Again, I think this is just good to make sure we haven't developed any bad habits, catch any errors. What I'll also draw on here, though, and if you want to do this on your own paper in a different color, remember we're running almost like a double test at the exact same moment. Because we also want to test it against the 1% level of significance. And again, this is where I think a visual is super helpful. You can see here, it's almost the same thing. We're just a little more extreme with the 1%. With the 5%, if our data value would fall in here, we'll reject the null. The 1% says the exact same thing. It's just a little more extreme for that sample mean. We know in doing this that while we know that 615 is somewhere on this curve, we know it's to the right of it, but it's somewhere on this curve. We don't know those cutoff values, aka the critical values. How do we find those? We're going to look at the standard normal curve. Because our distribution of sample means is normal, we can easily transition it to the standard normal curve, which is a mean of 0, standard deviation of 1. Again, for visual sake, I'll draw the same illustration. And what we need to do is to find both of those cutoff points. Okay, the one in red will be for the top 5% of our data. How many standard deviations do we need to go away from our mean to be in the top 5%? And how many do we need to go to be in the top 1%? Again, not much should be new here. How do we find those critical values? Well, how do you find any value on the standard normal curve? When you know the amount of area. Again, the red being 5% and the green being 1%. Inverse norm. But we'll need to run it twice. Not because it's two-tailed, but because we have two levels of significance. We got to find two cutoff points. First one, we're going to ask ourselves, as we always do with inverse norm, how much area is to the left of the data value I'm interested in? Well, if this red area is 5%, 95% is to the left of it. Mean and standard deviation on the standard normal curve is 0 and 1. Same concept, except now it's going to be 99%. 0 and 1. When we run these, I get 1.645 and 0.99. People who worked ahead of me, is that what you got? Okay, and then 2.3. 3, again, people who worked ahead of me. Perfect. Again, for your visual sake, if you're drawing a picture, which I think can be super helpful, that's what we're looking at. We have two cutoff values. So what we're really going to do now, we kind of had to double dip there, but the test statistic, that's just where we transfer our sample mean, which was 615. We transfer it onto the standard normal curve because that's where we know the cutoff values are. We transition it, again, if you've forgotten, using this formula. That's how we find where 615 is on this curve. That's the formula we use. Our mean, again, we're assuming 576 to be true. So 576 will act as our mean. Standard deviation was 120 divided by the square root of 36. And when we run this, 615 minus 576, 120 divided by the square root of 36. I got 1.95. Is that what we got? People who are ahead of me? Perfect. And again, what does that mean? I think that's where the visual is helpful. Well, we're going to see 2.33 was this cutoff for green. 1.645 was the one in red. Our value is going to fall somewhere right in the middle there, probably a little closer to the, actually pretty much smack in the middle of those two. And then again, because I think the visual is helpful, I'm not going to scroll down, but the bottom two steps would be 7 and 8. So when you see this visual, what you should be thinking in your brain is, if I do them one at a time, so at the 0.05 level of significance, we are going to reject the null. Again, right now we're not going to worry about writing conclusions. We'll have plenty of time to do that. We did that in 10.2 plenty. We are rejecting the null here, right? Our data value, our test statistic, 615 is in that top 5%. We know that because on a standard normal curve, if you are beyond 1.645, which we are, you're in that top 5%. So we reject the null. But at the same token, at 0.01, we are not in that green shaded region. If you can visually almost imagine the red area is not there, we'd be in the white, right? We're not in that extreme 1%. We're somewhere between. So at a 1% level of significance, we fail to reject the null. Again, none of this should be new to you. What you should begin to see, though, whether maybe this is a helpful review for you or this is something that you're like, man, I've got this in the bag. Why are we doing this over again? We can see our test statistic is somewhere in between. It's not in the top 1%, but it is in the top 5%. Maybe it's the 3%. Maybe it's 4%. Typically, we've been using these significance levels. But what if I said alpha was 0.03 or 0.02 or 0.04? Would we end up rejecting the null? What you can see really, really quickly is that if I keep changing the significance level, it becomes incredibly tedious to run this test over and over and over and over and over again. So in stats, we have a way of combating that. We've learned the general way to hypothesis test, but what we can see is where our way of testing falls short is it gives us a cutoff value and it gives us R value. And it simply tells us, did we fall in it or not? But then if we want to see a different significance level, in other words, if our cutoff point changes, we have to do more work over and over again. So how could we limit doing that work? In other words, you don't need to write this down. This is just the idea. At different levels of significance, as you just saw, we may change our decision of whether we reject the null or not. So the question becomes, for any level of significance, will I reject the null? Given my specific value, 615, which turned into 1.95 on the standard normal curve, will I reject the null at a 2%, at a 3%, 4%, 5%, 6? You get the idea, level of significance. And how can we do this without just continually running hypothesis tests? Well, the answer is going to come from re-looking at levels of significance. So here's what we're going to look at. Let's go back here. And if we look at a 5% level of significance, 5% level of significance, right? We're on our standard normal curve. This is some cutoff. Actually, we know what that is. It's 1.645. The level of significance is an area. Okay, it is a specific amount. And what we said was if our data value fell in it, we would reject the null. So when we got a data value like 1.95, we said we would reject the null. This was our test statistic. But we asked ourselves, if that blue line moves, how do we, again, are we going to have to rerun the whole test? We'll know if we start thinking about what's in red in terms of an area. You see, Much like the 1.645 is a cutoff for my level of significance, where it says 5% is beyond, we can imagine the red line is a cutoff as well. Thus, if we find the amount of area that is to the right of my test statistic, if I find out how much area that is, and I compare it to my level of significance, now I no longer have to run multiple tests. How would I do this? Well, think about it. How do you find an area given a data value on a normal curve? Again, think about that for a second. What we've done so far is we've had an area and wanted to find a data value. When we have an area and we want to find a data value, we use inverse norm. What I want you thinking about is, now that we have a data value, we've got this test statistic of 1.95, how do I find the area? Okay, I'll give you 30 seconds or so. Write down if you know the formula to use on your paper. I want to find what this red area is. I have a data value. I know the cutoff point. How am I going to do that? What I hope you have come up with is normal CDF. We started doing this in chapter 7. We know that if we have an area, to find a data value, we use inverse norm. Norm CDF, though, is the opposite. We have a data value, and we want to find an area. So if we look at this example here, where we have 1.95, and I want to find all the area left of it, or to the right of it, excuse me, my left, your right, I'm going to use inverse norm. So let's go ahead and do it. Remember, NCDF requires left bound, right bound, mean standard deviation. The mean and the standard deviation are going to be 1 because we're working with that standard normal curve. What's my upper boundary going to be? Someone tell me, what should this upper boundary be if I'm going to be greater than 1.95? Anyone remember? What do we plug in here? Left bound, right bound, mean, standard. Yeah.
Is it the 1E99?
Very good. 1E99. Right? When we work with the norm CDF, 1E99 is the way of telling our calculator infinity. Right? Our calculator can't physically process infinity, so we just put in a massive number instead. So when we run this, and check my word, I got 0.026. Is that what we got? 0.026. I'm going to rewrite these as percentages. So here's the big idea. Here's the concept of this is what all of 10.3 is about. So don't miss this. What we just did in the example above is we tested against a 1% and a 5% level of significance. We found that we would reject the null if we ran with a 5% level of significance, but not with a 1%. So the question became, if we wanted to compare our specific value to a bunch of different levels of significance, do we have to keep running the test? Answer, no. So how do we do it? Well, again, we know here, we can see visually with the 1.95, if I have a significance level of 5%, I'm going to reject the null. It's not a question, right? The 1.95, where my data value fell, is being rejected at a 5% level of significance. But what we can start thinking about is, how could I test this against any level? Well, what we do is we view this 1.95 as a cutoff point. We find how much area is to the left of it. In that case, we did it by using NCDF. It's 2.6%. The other way of thinking about it, if alpha is the top 5%, there's only a 5% chance, given that the null is true, that my data value falls in that top 5%. Will I end up rejecting the null? Well, yes, in this case, because the value I got has only a 2.6% chance occurring. We're rejecting the null if our value has less than a 5% chance of occurring, and ours only had a 2.6% chance. This is the probability, this area, this 2.6% is the probability of getting a sample mean at this level or greater. So then if I ask you, are we going to reject the null at a 1% level of significance? Well, now that you know this amount, it's really simple. No, I'm not going to reject the null. I would fail to reject it, which again, we saw in the example above. Why? Well, visually, 1% is going to fall about here. But practically, 2.6 is bigger than 1%. Okay, it is not, if I'm looking for the top 1%, well, my data value is in the top 2.6%. So no, I'm not going to reject the null there. This is the idea of 10.3. That value, that area, that 2.6% is called the p-value. And there are two explanations for the p-value. They sound very different, but they mean the same thing. The p-value is the probability of a value as extreme or more extreme than our test statistic occurring, given that the null hypothesis is true. And if you want a visual of that, we had that 1.95. That was where our specific data value fell on the standard normal curve, how many standard deviations it was from the mean. The p-value says, what's the chance that if we calculated another sample size of 36, what's the chance that that value, that sample mean of those 36, is beyond 1.95 on the standard normal curve? At it or beyond it. What's the chance that that happens? As extreme or more extreme, given that the null is true. Here's our cutoff. It says, what's the chance you get a data value in the blue region? If we ran the whole thing again of 36 samples, what's the chance my sample mean is at 1.95 or beyond? Now you also have this alternate explanation. The smallest level of significance for which the observed sample statistic tells us to reject the null. While these look very different, they're saying the same thing. We have our specific value, and what we're going to do is find the probability that if we ran the whole thing again, a value as extreme as ours or more would occur, aka this blue region to the right. That gives us a percentage. There's a 2.6% chance I get a value as extreme as 1.95. Now, why does that double as the smallest level of significance? Well, you saw it in the picture above. If that percentage is less than your level of significance, you're going to reject the null. If my cutoff point is in the top 5%, if the top 5% I'm rejecting the null, and the probability of a data value as extreme as mine occurring is 2.6%, well, then I'm in that top 5%. If it's 1%, my cutoff's 1%, and there's a 2.6% chance my data value occurs, then I'm not in that top 1%. So what we're going to do, where we're going to edit our hypothesis testing process, is we are going to start calculating p-values. No more are we just going to find our cutoff point, find our data value, did it fall beyond it? Because then we have to keep running hypothesis tests for different levels of significance. In general, the practical thing, if you're like, man, Mr. Carter, I am lost in the theory. This is not making sense. It's like you're talking in a foreign language. Here's what you got to know. For the practical calculation side of things, if your p-value is less than your level of significance, you will reject the null. The p-value, yes, sir. Mm-hmm. The p-values like Google Translate. You can compare it to any level of significance and know whether you will reject the null or not. That's the beauty of the p-value. That's why we're learning it. I don't want to keep running the test over and over again. I want to know if at any level of significance, am I going to reject the null or not? So if your p-value is less than the level of significance, you're rejecting the null. Think about the example above. 2.6% is less than 5%, we reject the null. If your p-value is greater than the level of significance, you're going to fail to reject the null. 2.6% is bigger than 1%, so you fail to reject the null. Your level of significance acts like a percentage, saying, I want your data, there's enough evidence to go with the alternative if my data value is in the top 1%. So we find the p-value. If the likelihood of my data value occurring is bigger than that top 1%, well, then we don't have enough evidence. If it is less than it, then we do have enough evidence. So let's do an example. Okay, again, if you want to go ahead and try this on your own, be my guest, grab the important info, and go for it. Last year, the average age of students attending Fremont College was 21.3 years. This semester, in order to meet the needs of older students, more classes were scheduled during the evening and weekend hours, as the average age of students at Fremont College increased this semester. And so the question, they took a random sample of 64 students. Average age was 22.1 years. Sample standard deviation, 2.7 years. We want to use the p-value to test the hypothesis that the average age of students this semester is higher than it was last year. For this example, we use a level of significance of 0.01. For those of you who want to do this on your own, I'll give you about a 30-second head start. And if you're still unsure of quite what you should be doing, stick with me. Okay, let's identify our known information. The average age of students was 21.7. However, the group we sampled had an average age of 22.1 years, with a sample standard deviation of 2.7 years. They took a sample size of 64 students, which means that our sample standard deviation also equals our population standard deviation, allowing us to run this hypothesis test. We'd have to use some alternate methods if our sample size wasn't big enough. The mean of that sampling distribution, again, the same as that population mean, standard deviation, 2.7 divided by the square root of 64. And I get 0.338. Okay, this is our important info. Again, we're mentioning in your brain, I want you to have a little asterisk there. That is not the population mean at this moment. That is the traditionally held value. It's what we're assuming to be true. Again, we don't know the population mean at this moment. We're just going to make the decision as to whether we have enough evidence to say that 21.7 is still the population mean, or if it might have changed. Null hypothesis, nothing new. That average age is still 21.7. Their offering of evening classes did not incentivize more older students to come. The average age has not changed. Nothing to see here. Nothing new. Again, don't do this based on your test statistic, but if we read the language of the problem above, they want to see if their average age has increased by offering more of these evening courses, maybe for working adults. So we want to see if that 21.7 went up. Do we have more older students attending the school? That should be your alternate hypothesis. Again, this part should not be new to you at all. You should be experts at this point. Level of significance. We said we're specifically going to look at 0.01. Again, I'm not going to spend the time looking at errors right now. Type of test, again, because of the alternate hypothesis being a greater than, we want to see if that average age has increased. We're looking at a right-tailed test. Now is where, again, if you're working ahead, I would pause at this point, make sure you're doing this somewhat similarly. Now it's where we shake it up. Okay, this is where we're going to do things a little differently now that we understand the p-value. So again, the picture you're imagining, right? This is the distribution of all the sample means, smack at the middle. We're assuming the null is true. So we assume the mean of all these sample means equals the population mean, which is 21.7. We're assuming that population mean is 21.7, which means that it's right at the heart of the mean of our sample means. What we are looking at now is we are going to jump straight to finding that test statistic. Okay? I know that, and if we look back, that sample mean was 22.1. 22.1. So I know it's somewhere in the right half. But again, to find the specific value for it, I'm going to go to that standard normal curve. And I want to see where 22.1 falls on it. So we do 22.1 minus the mean we're assuming to be true, divided by the standard deviation. In this case, the sample standard deviation, though it's the same as the population. We run this calculation. And we get 1.185. No, I typed something in wrong. Yep. I typed in a wrong number. We should get 2.37. That should be 21.3. That look better? Okay, 2.37, perfect. Okay, I'll pause a second if you're catching up. So where 2.37 is it's over here, right? It's obviously on the right side of our curve. Again, practically, what does this mean? 22.1 is 2.37 standard deviations above our mean. 22.1 is 2.3 standard deviations, 2.37 standard deviations above our mean. And this is where we're shaking up this process. Now what I'm going to do is I'm going to find the chance, the probability of getting 2.37. Okay, what are the odds that if I ran this whole thing again with the same sample size, I would get a sample mean as extreme or more than 2.37? Now be very careful. When I say as extreme, I don't mean either end. That's based on the alternate hypothesis. In this case, extreme is the top percent. So we're going to calculate that p-value now. What are the odds that 2.37 or a number bigger than it, because it's right-tailed, occurs again? Well, if I want to find the probability that I get a value as extreme or more, I'm going to go from 2.37 to infinity. And again, the mean and standard deviation of that standard normal curve is 0 and 1. And when I do this, I get 0.0089. Is that what you all got?
Yes.
Okay, so what does that practically mean? Again, my picture is not to scale, right? That value should probably be over a little bit more. But this value, if I turn it into a percent, is 0.89%. That means that not only is this area to the right 0.8 or 0.0089, but there's a 0.89% chance that I get a value as extreme or more than 2.37%. Now what you do is you think about your level of significance. Our level of significance was 0.01. In other words, 1%. So when we think about this, if our significance level is 1%, if my cutoff point is the top 1%, and there's less, it's 0.89, but a less than 1% chance that I get a data value that extreme, am I going to reject the null? Yes, absolutely, right? My cutoff point is somewhere to the left of it because my cutoff point is 1% of my data. But if only 0.89% of my data is to the right of my value, then I have to be in the 1%. So in this case, we will reject the null. Again, if you are someone, I know this can be a lot. I know it's very lecture driven. I know it's not a lot of you talking and a lot of me talking. But if you're someone who's somewhat lost, look back at the practical, what do we do in each problem? Your p-value was less than your level of significance. That's why we're rejecting the null. The probability of getting 2.37 is less than 1%. It's 0.89% to be exact. Now again, if you're sitting there going, Mr. Carter, we just learned a whole process for doing this. Why are we doing it this way now? Because the beauty of this number is that I could not only compare it to 1%, but if you said 5% level of significance, I'm still rejecting the null. 2%, still rejecting the null. 0.9%, still rejecting the null. Now, the minute our significance level goes below 0.89%, so if you, for some odd reason, tested at a 0.8% level of significance, now I no longer reject the null. That's why this method is a little better. I can compare it to any level of significance. So in this case, we would reject the null. Again, for now, I'm not going to get into the conclusion side of things. But again, that's the process of testing with a p-value. Okay, one more example to do. Again, I know it's been a long day, especially for a Monday. I know this is a lot. I know it's not the most fun thing in the world. But we got one more to do. And then tomorrow will be more problem-solving example, work with other people based. So just hang with me. I know it's not the most fun thing, but I think you'll get it as we keep going through. If you want to go ahead and try this on your own, be my guest. My advice, though, if you're someone who likes to work ahead, be very careful when you get to step 5 and you start doing the test statistic and the p-value, because this example will be a little bit different. Okay, it can get a little bit tricky. What construction company figures the cost of a project based on average idle time of 68 minutes per 8-hour shift? Blah, blah, blah. New work schedule has been completed by the construction foreman. Not known whether this schedule will change. We've seen this word before. Change idle time or not. Determine if the new schedule changes the average idle time. A random sample of 49 workers was observed. Average idle time was 65 minutes, standard deviation of 10. Use a 5% level of significance. Does the new schedule change idle time? We're going to use a p-value to make the call. Basically, in a big problem like this, what are we imagining? They want their workers to idle around less. So they come up with a new schedule. They want to see if that new schedule changes the idle time. Again, change, there's no indication, despite this value here of 65, there's no indication of whether we want to go up or down. We just want to see how the new schedule affects the time the workers are hanging around. Population mean traditionally has been 68 minutes. Again, we don't know it exactly at this moment, but this is what we'll end up assuming to be true. Sample mean, when we looked at the 49 workers on that new schedule, their average idle time was only 65 minutes, so a slight decrease. Again, sample size was 49, which is a big sample. Standard deviation was 10 minutes. Again, that equals the population standard deviation. Mean of all those sample means is also going to be 68 because we're working with a large sample. Standard deviation of the distribution of sample means will be 10 divided by the square root of 49. And we get 1.429. Null and alternate hypothesis. What we're looking at here, 68, right? We assume the new schedule hasn't affected anything. New schedule doesn't really impact the amount that the workers are standing around. Your alternate, it's not equal to 68. Again, this is where we have to be super careful, right? Just because the new schedule in our sample dropped from 68 to 65 doesn't mean it's a less than or a left-tailed one. They just want to know if the schedule changed the amount of idle time. That means we're looking at whether it grew or whether it dropped. We just want to see if something changed. Level of significance, they're going to have us look at a 5%. But again, the beauty of the p-value, we can look at any level of significance. Potential errors, again, we've looked at that plenty, so we'll skip that for now. Type of test, two-tailed, because of our alternate hypothesis. We're just trying to see if the schedule changed idle time. Is the average different than 68 minutes? Now we jump to finding the test statistic. Again, in 10.2, we would go ahead and find the cutoff areas, but since we're finding the p-value, we don't need to do that. We're just looking at the test statistic. So if I look at the distribution of sample means, of which my assumed population mean is in the middle, what we're going to look at is where does my test statistic fall? Okay, I assume since my sample mean is 65, it's going to be somewhere in the left half. Okay, but I don't know specifically. Because in order to find that, I have to know how many standard deviations away from the mean I need to go. To find how many standard deviations away, you look at the standard normal curve. Where does my data value fall on the standard normal curve? We use this formula. I got negative 2.10. Okay? So our data value, negative 2.10 is here. Right? We're that many standard deviations below the mean. Now this is where you got to be careful. And this is the new part when it comes to calculating the p-value, right? The idea here, when we think about a p-value, and don't miss this, when we think about a p-value, right, it's the probability of getting a value as extreme or more extreme, right? We want to find the probability that something is 2.1 standard deviations. Now, in the previous example, we wanted to know that many standard deviations above the mean because it was a right-tailed test. But with this being a two-tailed test, when we think, what's the probability of getting a data value that extreme, we have to consider both tails. It's a two-tailed test. So we not only need to consider what's the chance of getting a data value 2.1 standard deviations below the mean, but also 2.1 above the mean. Why I hope this makes sense is think about when we're running a two-tailed test in the past, in 10.2, when I ran a two-tailed test, then I would find those cutoff values. In this problem, we're running a 5% level of significance. What you would do is you would split that 5% between the tails, right? And 2.5% would be here, and 2.5% would be here. It's the same logic here, right? Because I'm running a two-tailed test, My test statistic is going 2.1 standard deviations below the mean, but I'm just looking at extreme on either end. When I find that p-value, the probability of getting a value as extreme, I must also consider the idea of being 2.1 below and 2.1 above. Okay? We only do this for two-tailed, right? We run one-tailed just like we did before. So how do we calculate that p-value? Well, we're looking for the probability of being 2.1 standard deviations below and 2.1 above the mean. In other words, we're looking for this area. Well, how am I going to do this? Well, the beauty of this is the actual calculation is not that different. For now, let's pretend that this guy isn't here. Okay, what would we do for a one-tailed test? What would we be doing? Well, if it's one-tailed, what we're saying is we want to know the extreme lower end, right? In other words, we're looking for this area. How am I going to find this area? Well, I'm going from negative infinity, right? I'm coming all the way from the left up to negative 2.1. And I'm on the standard normal curve. So what's the probability of getting a value that extreme? I got 0.018. Okay? There is a 0.18% chance that your data or this area is 0.18%. There's a 0.18% chance of getting a data value, assuming the mean is true, as extreme as negative 2.1 or more. But what we said is we also have to consider the top percent, right? Just like our significance level splits on two-tailed tests, so does our probability, because we're going to compare it to the significance level. Now, where this gets really, really nice is your brain might go, okay, well, I'm going to have to run NCDF again. And I'm going to have to do 2.1 to 1E99, 0, and 1. But there's actually an easier way. This will get you the right answer, but there's an easier way to do it. When we look at this normal curve, it's symmetrical, right? So the amount of area here is the exact same as the amount of area here. They're equal because it's symmetrical. Therefore, if there's 0.18%, there's that much area here. There should also be that much here. Therefore, for a two-tailed test, what do? Well, all we simply need to do is multiply by a 2 out front. When you're running a two-tailed test and you're trying to find the p-value, the probability of getting that extreme, multiply by 2. When I do that, I get 0.036. 0.036. In other words, 3.6%. There's a 3.6% chance that I get a data value as extreme as negative 2.1. In other words, 2.1 below and 2.1 standard deviations above the mean. When you run a two-tailed test and you're calculating the p-value, whatever you get, multiply it by 2. Again, this goes back to the idea that this curve is symmetrical. And so the area here is the same as the area here. Again, what we're going to do with this value is remember our level of significance. Alpha was 0.05 or 5%. So I'll give you 30 seconds. Think to yourself, are we rejecting the null here? There's a 3.6% chance that I get a data value. If I ran the whole thing again, there's only a 3.6% chance that I would get a data value that's 2.1 standard deviations below and above the mean. Does that mean I would reject the null if my significance level is 5%? Again, what I hope you come up with is yes, you should reject the null. The probability of your data value occurring is less than the level of significance. If we want to be in the 5% extreme, we certainly are there. Again, the beauty of the p-value, if I asked you, what about 1%? Well, you tell me no, you'd fail to reject the null. We're not in that extreme 1%, but we are in the extreme 5%. Again, please understand, I empathize with you. I know this is a bulky listen. I know there's not a lot of talking, working together, stuff like that. We'll do more of that tomorrow. If you are someone who's sitting there going, I feel pretty dicey about this, what we'll do is starting class tomorrow, we'll summarize this, okay? I'll give you a little chart that tells you, wait, when do I multiply by 2? Wait, when do I go negative 1e99 to my value or my value to 1e99? We'll do that tomorrow and give you a chart summary. Go ahead and pack up. I'll spray your desk again. Thank you for your attention. I know it's not super fun, but I think you'll get the hang of it. If you're missing 10-2 for me, if you didn't get that done, and after today you are still very confused, set up some time to meet with me so I can help you out. Okay, thank you.
No.